So in this video, we're going to be talking about the carbon cycle across land, sea, and air. This will be the crucial backdrop to understand how CO2 released by human activities will affect the planet. But in this video, we'll start with the basics. We'll compare carbon uptake in pure water versus natural waters, like seawater. And we'll identify links between the carbon content of the oceans and weathering on land. Finally, we'll trace the journeys of inorganic and organic forms of carbon across the Earth's surface. We often imagine the carbon cycle as a singular journey of carbon from land, atmosphere, ocean, and back again. But in fact, there's two different versions of this. The first is the inorganic carbon cycle. This is primarily dealing with carbon dioxide, rocks, seawater, and calcium carbonate. And then there's the organic carbon cycle. And that's concerning carbon dioxide again, but its transformation into biomass via photosynthesis, and then the breakdown of that biomass into detritus, and the consequences for oxygen in the atmosphere. So our atmosphere today has around 400 parts per million of carbon dioxide. Most of the composition of the air, as we talked about earlier in the class, is nitrogen, oxygen, and argon. But 400 for every million molecules of air is the CO2 molecule. Within a pocket of air, CO2 is flying off in a bunch of different directions. It can go this way, it can go that way, it can hit walls and bounce off and ricochet. But then if you add a cup of pure water, some of the CO2 will hit the water surface and dissolve. Now, once it does, there's two chemical changes that can happen. The first is the transformation of CO2 in a gas phase in air to CO2 in a water phase. It's dissolved CO2. You can imagine the carbon dioxide molecule surrounded by water molecules on all sides, and it's sort of being held in place. Now, in pure water, there's this other reaction that can occur where the CO2 actually bonds with the water molecule, forming H2CO3, or carbonic acid. When you have pure water, this doesn't form very much, so only about 0.2% of carbon dioxide that dissolves in seawater will form carbonic acid. And if you add up these two pools, you'll have around 0.5 milligram of carbon per liter. And while this amount may be steady, it's really a combination of these series of forward and back reactions happening simultaneously. CO2 that's in this water is constantly leaving and returning to the atmosphere, and new CO2 from the air is constantly flying around and sometimes landing into the water and dissolving. This dissolved CO2 is constantly reacting with water and then constantly breaking apart. And so this process is referred to as chemical equilibrium. And so if you let this glass of water rest for a while, a few hours to a few days, you'll find this constant composition of carbonic acid, dissolved CO2, and carbon dioxide in the air. But if you repeated this experiment in an environment with lots more CO2, then you'll force more carbon dioxide into water. And this will be proportional. So if you have 6 times more CO2 in the atmosphere, you'll probably have around 6 times more CO2 dissolved in water. This is just because this reaction that's pushing carbon dioxide into water is happening 6 times more than this leaving reaction. So ultimately, this inventory of dissolved carbonic acid and dissolved CO2 increases by around a factor of 6, a similar amount to the increase in atmospheric CO2. You can think of this process as really similar to what happens when you're making soda. In that case, you're taking pure CO2 and you're forcing it into water. That establishes equilibrium with this high CO2 environment trapped in the air in your soda can. And then when you crack it open again, you'll have this rush of CO2 out into the gas phase, and you'll return to this type of equilibrium. And you have a lot lower carbon that's dissolved in water. This is the soda going flat, essentially. But when we compare this really simple example with pure water to the ocean, we find the ocean has a lot more carbon, even though both this pure water and ocean water are in equilibrium with the same amount of carbon dioxide in the air. So there's the same force of carbon going into the water in both cases. But in the ocean, there's around 100 milligrams of CO2 per liter of seawater, whereas in pure water, it's only around 0.4 or 0.5 milligrams per liter. And this is ultimately a really key process in the carbon cycle. Without this process, we would have a much higher CO2 in the atmosphere. So how does the ocean get so much carbon in it? To figure that out, we need to change the scenery. We need to go upland to the mountains. This is a picture of the Andes. It's very useful because you can see not only this fresh exposed rock here and these peaks, but also these pools of glacial lakes where water and freshly weathered material can interact. So we can simplify this complex interaction into a couple key chemical reactions. The first thing to know is most of the elements that will end up forming the major components of sea salt, calcium, magnesium, sodium, potassium, represented as K, all of these are found in oxide phases in igneous rocks. And so really you can think of the form here is that this calcium 2 plus is bonded to this O2 minus. There are two sodium single plus atoms that are bonded to the O2 minus oxide in rock. But when the surfaces of these minerals are exposed to water, this O2 minus doesn't stick around. And so the reaction follows this equation where calcium oxide plus water equals calcium 2 plus ion plus 2 hydroxide molecules. And this is going to be really key. You can see in each case for magnesium, sodium, and potassium, there's very similar reactions that happen. They're all generating this hydroxide. Hydroxide in water is basically the opposite of acid. And when you combine hydroxide with free protons, which is a definition of acidity, you neutralize both and you create water. So this reaction is happening both at these peaks during snowmelt, but also in these glacial lakes where freshly weathered material can interact with a whole bunch of water. At the same time, the same dissolution reaction of CO2 into water is happening here too. So in these lakes, you'll have atmospheric CO2 dissolving in to water to form this dissolved CO2 pool and this carbonic acid pool. So in our pure water case, that was the end of the story. But in natural waters, there's this new reaction that happens. And this is because of the hydroxide that's formed during the weathering of rocks. This hydroxide will react with carbonic acid. Essentially, the OH will steal the hydrogen from carbonic acid and leave behind this ion bicarbonate, HCO3 minus. Notice this is a new pool of carbon that wasn't available when we were just considering pure water. It'll also generate a water molecule, which we can kind of ignore. And as more and more material dissolves, you might have an excess of hydroxide relative to this carbonic acid. And then you can form this different reaction where these two hydroxides steal both of the hydrogens from carbonic acid, and you're left with this carbonate, CO3 minus. Slightly different than the first case, but both of them are significant. And so in the natural freshwaters, the addition of hydroxide, a base from rock weathering, enables more CO2 to dissolve in water. This is because we created this whole new pocket of bicarbonate and carbonate. And so CO2 will dissolve from the atmosphere into water, it'll form carbonic acid, and then it'll form carbonate. And because these pools are depleted now because they've been shifted into carbonate, more CO2 will dissolve into water. And this is what allows these freshwaters to hold significantly more water than just pure water. And this is the same thing that happens in the oceans. So we can just compare the sizes of these reservoirs so you can see what I mean. If you just consider dissolved CO2 and carbonic acid in both pure water and in ocean water, they're the same amount. They're really governed by the same backwards and forwards reactions of CO2 dissolving in water and CO2 leaving the water back to the atmosphere. But because the oceans accumulated all of this chemical weathering products over thousands to millions of years, there's this whole pool of bicarbonate and carbonate that can be filled out too. And so more CO2 will invade seawater and take the form of bicarbonate and carbonate compared to pure water where this pool is really tiny. We can summarize this whole series of reactions by a relatively simple equation. If you take water and two CO2 molecules, a calcium oxide group, this could also be a magnesium oxide or sodium oxide or potassium oxide, any of those. But if you take these components all together, you can generate a calcium ion that will stay in seawater for quite a long time, and these two bicarbonate atoms. So now we have a process to add lots of carbon to seawater. But if this was the only thing that was happening, you would just accumulate more and more carbon in seawater over the billions of years of Earth history. At a certain level, the amount of calcium and bicarbonate in seawater will become supersaturated. This is what allows coccolithophores and corals to precipitate these calcium carbonate shells that are so key to their life strategies. So you can see this reaction happening in seawater. Calcium 2 plus and bicarbonate are combining to form calcium carbonate. Because calcium is actually pushing out these two hydrogen groups, you'll also generate a CO2 and a water in return. And so this is a bit counterintuitive at first, but the production of these calcium carbonate shells, it removes carbon from the ocean by precipitating calcium carbonate, which can sink to the seafloor. But it can also generate CO2, not bicarbonate, CO2, that can then exchange with the atmosphere again. So this is how the ocean loses carbon. And just to add that this reaction here is really a sum of two separate reactions. So you can see calcium plus one bicarbonate will make a calcium carbonate, and it'll make a hydrogen ion, which is essentially an acid group. This reaction makes acid. This acid will then be neutralized by another bicarbonate ion, and this is what forms carbonic acid, which will then dissociate into CO2 and H2O. So we've written one summary equation to describe the weathering of rocks that consume CO2 and puts it in the ocean. We've written another equation that describes the removal of carbon from seawater through precipitation of calcium carbonate. What you'll notice here is that the second equation generates water and CO2, which are reactants or inputs in this first equation. So if we add these two equations, these two and these two will cancel out. So we can write a simplified combined equation where calcium oxide, remember this is just representing material in rocks that will dissolve easily. Calcium oxide plus CO2 generates calcium carbonate. And this is the reaction that describes the inorganic carbon cycle really succinctly. Essentially, igneous rocks are reacting with carbon dioxide in the air and generating calcium carbonate that falls to the bottom of the ocean. Just add too that the net effect of this equation is to take CO2 from the atmosphere and bury it in marine sediments at the bottom of the sea. So we've described the system where the combination of weathering of rocks on land and calcium carbonate production in the oceans removes CO2 from the ocean atmosphere system, this combined interchanging system. So this is the main removal process of the inorganic carbon system. And to balance this, we need a source. So where does the CO2 source come from? And the answer is from deep within Earth. You'll remember when we were discussing the origin of water on Earth, we realized that volcanic gases had a lot of water content. And this was eventually a process that started to fill the oceans. At the same time, these gases have lots of carbon dioxide. They're around 10% CO2. So volcanoes like Kilauea and other hotspots like Iceland, basically every volcano is a source of CO2 to the atmosphere. And really the ultimate source of the CO2 is from Earth's mantle. So volcanic activity is a way of taking carbon dioxide that's still retained in Earth's mantle and allowing it to escape into the atmosphere. So we can summarize the inorganic carbon cycle as a series of interconnected journeys. We can start with CO2. It's been trapped in the mantle for billions of years. And due to volcanic activity, it can escape into the atmosphere. Some of the CO2 in the atmosphere will dissolve in the ocean, and some of it will fly right back out and return into the atmosphere. And ultimately, the major way it's removed from the atmosphere is by reacting with igneous rocks, calcium oxides, magnesium oxides, sodium oxides. This generates bicarbonate that then washes into the ocean. This is what allows the ocean to have such a large carbon inventory. This is all well and good until calcifying organisms precipitate calcium carbonate, which removes carbon from the oceans and collects in marine sediments. And it can stay here for millions and millions of years and then go on one of two different journeys. In the first case, it can be subducted back to the mantle in subduction zones at ocean trenches. And then the cycle would be complete. But there's this other thing that can happen too, where calcium carbonate sediments can be compacted and lifted back up onto land. This is what generates the White Cliffs of Dover in England, but it's far more widespread than that. Vast parts of Central America, Southeast Asia are composed primarily of limestones that are marine sediment calcium carbonates that have been compressed and formed back into this calcium carbonate sedimentary rock. This too can react with atmospheric CO2 and dissolve back into the oceans to repeat the cycle again. But the main inputs remain volcanic activity. The only permanent output is subduction back into the mantle. So far we've considered the carbon cycle as this transformation between carbon dioxide in the atmosphere to bicarbonate in the ocean to calcium carbonate in marine sediments. But there's this whole other side, and this is the organic carbon cycle. You've learned about this already when considering the life strategies of phytoplankton. But you can simplify all these ecosystems as conducting essentially two different chemical reactions. The first is the combination of CO2 and water through photosynthesis to create CH2O, which is just a simplified version of the equation for biomass. If you remember the equation for glucose, C6H12O6, this is just that divided by 6. This is a very simple representation of organic matter. It's not totally accurate. And in truth, there's really an infinite combination of not only these 3 elements, but also other elements that we associate with biomass: nitrogen, phosphorus, sulfur, iron, and lots of other elements too. The other key product from photosynthesis is oxygen. This is the air that we breathe. So the second reaction is just the reverse of the first reaction. This is respiration. This is the consumption of fixed carbon, of biomass, with oxygen to breathe out CO2 and H2O. And we know that this reaction is really key to creating the Earth that we all enjoy today, because the atmosphere of Earth is so different from that of other planets. So if you look at Venus or Mars, you'll see the atmosphere is mostly carbon dioxide with little amounts of nitrogen and argon. And this is really because the source for all of these gases is volcanic activity. And this is essentially the ratio of CO2 to N2 to argon in the mantles of not only Earth, but Venus and Mars. You can see there's almost no oxygen here as well. There's been estimates about what Earth's atmosphere would actually be like without life, considering that it's also unique in that it has an ocean, but still carbon dioxide dominates the atmosphere. And so you can see that the effect of actual life is to remove almost all of this carbon dioxide. 300 parts per million CO2 of the pre-industrial atmosphere is around 0.03%. And in contrast, oxygen in the atmosphere is around 21%. So this is a massive overturning of what volcanic activity alone would produce. But if you look at this equation again, right, if this is totally in balance, then you'll never really accumulate oxygen. If an organism generates carbon through photosynthesis and then someone else comes along and eats them, there's no accumulation of oxygen in the atmosphere. The only way you can have oxygen escape to the atmosphere is if some of this biomass is preserved for long periods of time. And the major way to do this is burying this carbon in sediments and rocks for millions and millions of years. So this is a sketch of the organic carbon cycle. Here, the main starting point is atmospheric carbon dioxide that's ultimately from volcanic activity, but also in equilibrium with the oceans. Now on land, atmospheric CO2 is taken up by plants and turned into biomass. The plants will release a lot of the CO2 back to the atmosphere, but the parts that they don't release will generally fall into the soil. You can imagine leaves falling off trees during the start of autumn, or tree trunks being turned slowly into topsoil. But the bacteria and fungi and animals that feed off the soil carbon eventually turn this back into atmospheric CO2. So this is the terrestrial organic carbon cycle. There's a similar one in the oceans, where we know there's this equilibrium between CO2 in the atmosphere and in the ocean. And this is the material that marine phytoplankton take up and form their biomass. So a lot of this, through heterotrophs and grazers and bacteria, returns back to CO2. So you have a similar cycle like you did with the land plants. But there's this very small amount that sinks to marine sediments and somehow manages not to be eaten by anything. One of the ideas behind this is that it's just stuck in between different mineral surfaces, so no one can really access it to eat it. And in these marine sediments, it can stick around for thousands of millions of years. Some of it will form back into CO2 and return to the oceans as inorganic carbon. But some will be preserved in sedimentary rocks for a long time. And this is actually where fossil fuels come from. Most of the oil that we use today originally was fixed by marine phytoplankton. And then today we have this return process where the fossil fuels go back to the atmosphere. Okay, so in this video, we've summarized the carbon cycle in its inorganic and organic forms. For the inorganic side, we've compared carbon uptake in pure water versus natural waters and shown how the weathering of rocks allows natural waters, like seawater, to contain a lot more CO2 than we would expect just on the diffusion of atmospheric CO2 into water. We've also combined a series of key equations to show how the weathering of rocks on land ultimately consumes atmospheric CO2 and buries it at the bottom of the ocean. And this is the major feature of the inorganic carbon cycle. We've also run through the organic carbon cycle, which is dominated by photosynthesis in one direction and respiration in the return direction. we've emphasized how some of this organic carbon needs to find its way into marine sediments in order for oxygen to accumulate in the atmosphere. So now that we've traced the journeys of carbon through these inorganic and organic loops, we'll estimate how fast this cycle turns over in the next video.